Hey, what's up, guys? This is Chung here. So today, let's take a look at this problem, number 907, sum of subarray minimums. So given like an array of integers a, find the sum of minimum b, where b ranges over every subarray, contiguous subarray of a. And since the answer might be large, return the answer modular by this number. So what does this one mean? What does this description mean here? Basically, it just asks you to find all the substrings of A. And for all the substrings, find the minimum number of each of the substring and then summarize that minimum number together. Okay, so for example, this one, we have like we have 4 elements, right? So in total, how many substrings we have? We have n times n minus 1 divided by 2. That's the total substrings we have, right? I think that's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's n times n plus 1 divided by 2. Anyway, this is irrelevant. Basically, so we're getting all the substrings here, right? And then for each of the substrings, we get the minimum numbers. So this is 3, 1, 1, 3, 1, 1, 2, right? And then we sum everything together, and the answer is 17. And this is the constraints here. So first thing first, right? I mean, a brutal way or a naive way is just to find all the substrings, right? So we do a nested for loop. We find all the substrings, and then we get the minimum value out of those substrings, and then we summarize them together, right? So that will be what? Will be like n squared times n, I think something like n cube, because we have a total of n squared substrings, and each of the substrings we need to get the minimum of it, right? So obviously this will TLE. And first, so that's why we have to find a better solution, which is what? So if you take a closer look here, as you guys can see here, so one, how many ones we have? We have 1, 2, 3, 4, 5, 6, right? So basically anything that's smaller than 3, sorry, anything that's smaller, any number is greater than 1 will be using this one as the minimum of minimum result number here. And how many substrings does this one can cover, right? So of course 1 is itself, and then what? And then 3, 1, 1, 2, uh 1, 2, 3, and 3, 1, 2, and 3, 1, 2, 3. Basically, of course, this one, 6 in total. So how do we get this 3 here? Basically, as you guys can see, we have 1 here, right? We have 3, 1, 2, 4. So basically, if we look at we put this one as in the middle, there are like 1 numbers on the left. There are 2 numbers on the right. So basically, this is kind of a combination, you know. So the combination is what? So on the left side, we have 2 numbers, and on the right side, we have 3 numbers. So the combination, okay, of course, we need to include this one itself. So in total, it's the total combination is 2 times 3. That's how we get 6. Okay, and the 6 is the number the one will have. The 6 will be the count of 1 here. So now we have 6 times 1, right? So that's the first one. And then basically that's 6 times 1 will be covering all the substrings that include 1. How about 3 here? So 3, as you guys can see here, we have 0 on the left. Of course, there's nothing on the right side who is smaller than 3. Sorry, who is greater than 3. So that's why we have only 3 times 1 here. Okay, so we have already covered 1 here. How about 2 here? So 2 we have 0 on the left, which means on the left side is 1. So we have basically we have numbers. So here's the formula: times left times right. So basically that's the formula for each of the numbers here. So when we add 2 here, right? So we have 2 times what? So on the left there's 0, which means this is 1, right? But remember, so it's always starting with 1. It's 1 based, okay? And on the right side, how many we have? We have, including the cell, we have 2. So we have 2 times 2 here. And for 4 here, 4 times 1 times 1, right? So that's how we get the final answer: 6 plus 3 plus 4 plus 4. So the total 9, 9, 13, and 17. So we have total of 17, right? So as long as you guys can find this pattern here, right? So now the next thing is how can we find for each number here? How can we find how many numbers on the left side is smaller than the current number, and how many numbers on the right is smaller than the current number, right? So that's gonna obviously gonna be a pre-processing. Okay. So then the next challenge is how can we efficiently find that? You know, if you cannot efficiently find that, it will be ending up with the same time complexity, because if you're trying to find the smallest number on your left with a naive way, right? Same thing. Let's say we have 2, 4, 6, 8, 3, and 1. Okay, if you're finding it in a naive way, which is at each of the location here, right? You loop through everything on your left. So that's obviously O n square, right? Then basically we end up with the same time complexity. But now the question is, how can we efficiently find how many numbers on my left is greater than I am? Okay, so next time when you guys see this kind of problem, you're trying to improve the time complexity from a scan to a to a O1, something like that. Always try to think about, the first thing is try to do the pre-processing, right? But for this problem, we are doing the pre-processing, and we are trying to improve this. mm, we're trying to improve this. And the second thing is the monotonic queue, which can be also used on this for this problem. So basically, so the monotonic queue is gonna, so in this case, we're gonna use like a called a decreasing queue. So we're gonna have like a decreasing queue here, right? So decreasing queue here, and all the numbers, all the elements in this decreasing queue has the has the number sorted in descending order. Okay, and besides the number itself, we'll also be storing the count for this number. So it means that how many numbers is smaller than this current number. So what does it mean? It means that we have 2 here, right? So basically the first element is this. Okay, I'm gonna draw a stack here. So the first is like the 2. We have 2 and 1. Remember, we're always like doing this 1 base thing. So and 2 here and 4. So now we have 4, right? So the 4 is also 1, because 4 is greater than the top one. Same thing for the 6, right? So 6 is also 1. And then we have 8, right? 8 is also 1. Now we have 3. So every time when we have this 3 here, if we check, okay, 3 is smaller than the top one. So what do? We pop these things out, right? We pop this out, and then we accumulate. Basically, we're gonna add these numbers to the current value here. So basically, this is 3. We have 1, 1, 1, right? So basically, this 3 will be popped out. And now the values for, and then we're going to push these 3's in. So what does it mean? It means that we have 3 equals to 4, right? And then the next time when we have at 1 here, so we're looking at this one number 3 on the top. Okay, so we know, okay, 3 is greater than me. So I know, okay, so I just need to get the count from this item, because this one basically is telling us how many numbers on the left of 3 is smaller than 3. So that's how we use this decreasing queue. There's Since 3 is smaller, while we're processing 3 here, since 3 is smaller than all this kind of stuff, so there's no need to keep those things in the queue here, because this one item can represent everything that's greater than him. That's how we improve our 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 scan to get to pre-calculate the smaller number of the current number, the count of smaller number on the left of the current number. Same thing for the right. It's just like we're still using the decreasing queue, but we are processing from the end to the beginning. So that's the only difference. Okay, so yeah, I think that's the only two things we need to be careful here. And let's try to start coding here. So I'm going to have like n equals to length of a, right? So I'm going to have a left. So left means the count on the left, which is smaller than the current number. So everything starting with 1, right? And then we're going to have a decreasing queue here. And so for me, I think I initialize this decreasing queue for the first element, because we always know the first element, right? So the value is a0, and so it's a0 and 1, right? So that's the starting point, and then in range of the 1 to n. Okay. So first we need to basically we need to for each of the elements here, right? We just need to update the decreasing queue here. So if the decreasing queue is not empty and the ai is equal smaller than the decreasing queue, then the first one, right? That's how we and of 0. So that's how we maintain this decreasing queue. And every time we pop that out, we know, okay, we find something that's smaller than the current number, which means that I'm going to summarize those counts that the item that got popped out from the decreasing queue represent to the current left I element here, right? So decreasing queue, we do a pop, and then the second element is 1. Okay. So like I said, since the current one will be including the previously one, so there's no need for us to keep this item in the queue anymore, right? Okay. And then after this we have find our current answer, right? And we just need to push this current element to the decreasing queue, so that later on so that the later number can use the values for this current number, right? So gonna be a I, and then the number is, of course, is the left I, right? Basically, this one means that what we're doing here is that, okay, we are telling we're putting this tuple into the decreasing queue. This tells us that at this number there are this this many numbers which is smaller than this number. So every time when you pop these things up, you can just use this number, just like just like what we're doing here, right? So that's that. Okay, so and for the right side, actually I can just copy and paste here. I will just do simple modifications here. So here it's going to be instead of I0, it's going to be a minus 1. So here I'm going to start from the n minus 2 because I already uh, set the last element. So that's why I start from n minus 2, minus 1, and minus 1. Okay. And oh, here, right here. So here's one more thing we need to be careful here. Since we're using like a less or equal for this left side, we don't want to use this equal again because that's to prevent this 1 1 1 case. Okay, this is because the this one, you know, this one can only be count for one side. Yeah, because if you're like doing this equal here, if we have like this 1 1 1 here, and we're at here, on the left side we have like we have 2, and on the right side we also have 2. So what's going to be the total here? So it's going to be 2 times 2, which is 4. But how many subarrays do we have here? 1 1 1 2. Hmm, let's see. So that will be a double counting, right? So for another example here, if we are like doing this equal on both sides, right? So at 1 here. So on this side, let's say we have at this side, so the right, right? So the right, if we're doing this thing on the for the right, so we have a right. So the right will be 3 because we're doing this equal here, right? So we have 1 2 plus itself, it's 3. And on here, the left is also equals to 3, right? So which means that, as you guys can see, so this 1 1 1 actually is one subarray. But if we're doing like this 3 for the right and 3 for the left, basically this 1 1 1 subarray will be counted twice, right? So that's why, we can only do this equal on for one side, which means that on this left, we either count this 1 1 1 by from with this left array, or we count it with the right array. We cannot do it for both because this is a one array because this is like the equal sign, right? Cool. So that's why we're gonna do like a equal here. Sorry, a non-equal here. All right. So now we have this this decreasing queue actually is just help us to speed up the pre-process of the left and the right uh, array here. So after this two for loop here, we have this left and right arrays we need. So the only thing left is just to calculate the minimum numbers, right? So for I in range of n here, right? And we have answer. Remember, so how we calculate these things? So we have the current number, which is a dot I, right? And we times the left I, and then we times the right I, and then just return the answer. Okay, run the code. And that's just so embarrassing. Sorry. Why it failed? I, I was pretty confident about this code, but the reality is so crucial. Mm, append decreasing queue here. Hmm. Oh, yeah, here. Maybe I should not have copied this code from above. Okay, so right. Okay, now it's correct. Submit. Oh, yeah, this is such a bad embarrassing. So it asks us to do the modular in the end, and I totally forgot about that. So 10 to the power of 9 plus 7. Okay, and then we do answer, do a modular of mod. Okay, so all right, and it's accepted. Cool. Mm, yeah, you guys can see here, we have a monotonic queue here, and for those who already knew this monotonic queue here, we have a O1 here because each element will only be pushed and popped from in and out this queue only once. So that's why when it's in the for loop here, we're treating this one as O1. So basically, the total time complexity for this is we have a ON here, right? Another ON and another ON. So in total, the time complexity is O of n. And the space complexity is, of course, is O of n as well, right? Cool. So that's it. I mean, the takeaway from this problem is that first, mm, if you got this problem in a real interview, first always come up with that brute force way, right? Basically, you get all the substrings and then you just get the minimum out of them and summarize the minimum. And the second one is try to find a way to improve it. So the way we're doing here is that you have to do some observations here, right? So I think it's kind of clear to realize that all the numbers, all the substrings, right? Basically, all the range this one can cover will be using this one as the smallest number, right? And after that, you just need to find, okay, how can we calculate this thing? So and then if you just write some examples here, you shouldn't be hard to realize that I just need to find how many number on my left and is greater than me and how many number on my right is greater than me. Now it comes down to how can you efficiently calculate this left and right array. We don't want to use the nested for loop. And then how can we improve that? So every time if you're trying to do some further improvements from ON to O1, always think about the monotonic queue, right? And then here's how we use it. Basically, we're storing two numbers, two two values in this monotonic queue, in the decreasing queue here, which is the numbers, the current numbers, and how many numbers on my left is smaller than me. Sorry, is greater than me. And then every time, if we are find the number which is greater than me, I can just uh, inherit the number to myself, so that we can remove that item from this queue, and we don't have to process these numbers again next time. And then later on, in the end, I'll just accumulate everything that I get from the number which is greater than me, and then push into here. Okay, cool. Yeah, I think that's it for this problem. Thank you so much for you guys to watch this video. Stay tuned. See you guys soon. Bye bye.